So our idea is that we're going to take this rectified, but still rapidly varying, actually at 60 hertz now times 2, 120 hertz signal, and try to make it DC. And of course the way would be to add a capacitor to even out this rectified signal. The important thing, if you attempt this circuit on your own, is to make sure that you use a large enough capacitor, which means a polarized capacitor, and that then you have to get the polarity in the correct way. And then we'll attach our oscilloscope here. So this would be our load resistor. Still yet to be determined what the load is, and that's actually one of the difficulties with that circuit we'll discuss in a moment. All right. We use a large capacitor for this, so this is one of the big ones that comes in the power supply kit. This is a 1000 microfarad. Notice a 50 volt capacitor. So this is the first time we've encountered this rating on capacitors or paying attention to it. Of course, capacitance we've talked quite a lot about. This is a really big capacitor, a millifarad, but has a high voltage rating as well, 50 volts. If you look at many of the electrolytic capacitors from last quarter, a lot of them simply do not reach 50 volts in rating. So these are sort of a special and actually slightly more expensive, typically, type of capacitor that can handle 50 volts. Why do we need 50 volts? Well, we've discussed this swinging voltage here is really more like plus minus 15. So you really have 30 volts, so a 50 volt rating should be sufficient. Very, very important, because now we're starting to deal with significant voltages and a fair amount of power. You absolutely have to get the polarity correct. So there's the minus sign and the short leg that goes on the negative side. That's going to be the ground here. So this is going to be the orientation of the capacitor. Then we're going to measure across the capacitor. So again, our oscilloscope takes the role of the load resistor, a very large load resistor, and then we have to connect this side of the circuit over to what will become the ground side as well. So I've just made this connection. And we can see we actually have done a very nice job of filtering out the previous oscillations into a flat level. How big? Well, I'm on 10 volts per division right now. As you can see, there's almost 2 divisions, so it really is about 16, 17 volts. Let's expand the scale a bit, and we do see there's some fuzz, there's some ripple still, and this would make you say, hey, maybe I need some more capacitors to filter at faster time constants, or a bigger capacitor, or so forth. And although this is a classic design, it suffers from the problem that we're measuring it currently with an oscilloscope with a very high internal resistance, right? When we measure with a scope, it's like measuring with a voltmeter. It has very high internal resistance. It doesn't change the voltage much of what we measure across it. It draws almost no current. And that means it's not emptying this capacitor very fast. If we started to have circuits hooked up to this power supply we've made, this DC power supply that we've made from AC voltages using the full-wave bridge rectifier, we started to draw current out of this capacitor. It's quite possible that the performance of this circuit would deteriorate. I'm not going to demonstrate that now, so we're going to use a related but somewhat different approach in our actual power supply for the project in this class. But that ripple is a sign that not all is great or perfect with this circuit that is quite functional. Again, how does it work in my head? What I think of is that the full-wave bridge rectifier, again, to sort of plot what's going on, voltage versus time, and think, okay, it's doing this, right? Right. Originally, of course, the circuit had looked like this. But we've rectified that away and flipped these up on top by our configuration of diodes. So this is what we have. When we put the capacitor in, the current starts to, it charges up, but the capacitor has some time it discharges, so I'll exaggerate it like that. And it pops up, and then as it drops, the capacitor starts to discharge like this. We recharge it, etc. So our final waveform ends up looking something like this, and this is the source of some of the ripple that we observe. A large enough capacitor with a big enough time constant means that the drop is increasingly small, and this really flattens out pretty nicely.